You must have seen time to time my videos where I talk about memory allocation, and also you must have heard multiple episodes I talked about why I generally don't use dynamic allocation, and there are instances I even trying to avoid stuff like linked lists and other stuff. So I thought let me show an analogy so that it gives some kind of architectural perspective. Okay, so I got here this stuff. This is like an ancient game which played in India. Sometimes they carve other than wood on the rocks itself, and then they can sit and play. Sometimes if you go to ancient temples in India, you can find this carving on the stone and rocks and stuff. Okay, so they use these shells. I got a few shells in this Tupperware. They use this shells like this, and they put in this slots, and they play. Okay, so something in this grooves, whatever you call. Okay, and they put, and then they move from one groove to other groove, and they play. Sometimes they even use this tamarind seeds as to play with this. Okay, so this is what. So they put several of them, I think 5 or something per groove. So I'm not much good in this. Anyway, what is the thing is this sort of each slot in this architecturally, if you see this represents like an array. The array can contain anything basically. Okay, it may be array of integers or array of structs or whatever it is, or it can be an array of pointers, and these pointers you can allocate dynamically, or else if it is a pre-allocated one, you can just link to this each pointer. Okay, so when you have an allocation like this, let's assume each hole is a thing in an array. So what happens is, as you can see, it has totally 1, 2, 3, 4, 5, 6, 7 to 14 grooves are carved, and when they want to store and they want to carry, what they do is generally they take this stuff, and you can flip like this, and then they carry. Okay, so this is what. So anyway, back to this. If you see here, there are totally 14 slots, and these are carved in this fashion. So these grooves are preset. So totally you are going to get 14 grooves. So same way, when you think about an array, the moment you start a process, it is allocating the memory, and that's the best part of it. So when you do such type of memory allocation, you know that there are so and so is the vacant slots, or else the array the array index, whatever it is, so the contents of the array. So with that, what happens is, let it be single dimension, multi-dimension, let's not bother about that. I mean to say, the advantage of memory allocation like that, and this is nothing to compare with any broader aspects of dynamic allocation and stuff. I'm saying the more of my videos, as you have following, I focus on architectural aspects. I'm not into teaching some student who is maybe in the college, or who is a fresher. Maybe he may not able to understand, because he need to know about this, he need to know about, he need to know about arrays, he need to know about dynamic memory allocation and several things. I mean to say, this video I just want to focus as usual for experienced guys, where you need to start thinking in a new way. So this is what. So when you use an array, what happens is, although it occupies so and so memory allocation, you can even do with the thousands of entries. So it statically allocates the memory space, but the advantage is it is up to you how much you want to use, and then this is predetermined. The problem comes is when you do excessive mallocs, or in the kernel space, if you do kmalloc or something, it puts a lot of strains and uncertainty in the system. Okay, so you should understand this uncertainty can be a factor of reduced performance. So if you want superior performance, you should not waste your time. Let's assume networking per packet, you should not do excessive allocation of SKB or something, and then you need to do that. So you need to have some kind of mechanism. I mean to say, let it be networking, let it be anything, let it be something you are doing in user space, let it be anything, let it be a group of bunch of IP addresses, let it be a routing table. This each slot can be an entry for a routing table, let it be anything. So when you have an allocation like this, always what is the advantage is you have preset count of available slots. Of course, this you can't scale it up everywhere, but on the other hand, arrays are far more advantageous, and I see often the problem is when they do the systems stuff, when they do the architecture, they still tend to follow something which is old and outdated, and they tend to follow something which is done long back, and they try to do the similar approach, whether it is a desktop application or else an embedded application or else even some type of a server large compute, high performance compute applications. So this is the approach we should change. If it is a question of high performance compute, you have tons and tons amount of memory space available, you may have even TBs of RAM available. So allocating any amount of arrays like this is not going to be an issue at all. You can do 200, 300, 2000, 3000, 5000, whatever it is. Okay, so you can do that sort of an allocation so that you don't have to do excessively. The problem with the linked lists is, see, you have to excessively do that, managing that, removing that, slots, removing that nodes. Okay, whatever you call a linked list is, cumbersome. When you do that, you need to do a lot of adjustments and other stuff. So this makes the code vulnerable, and it is, for saving some amount of memory space, you are adding a lot of extra code to deal that. Okay, and moreover, modern days no one writes any code to deal with linked list. Most probably some library you can use. Even in kernel we have several libraries which can deal the same. Even traversing a linked list, there are some libraries which you can use. So nowadays no one sits and writes any custom code, something like that. Most probably they will be using a library, but still, having said that, it has all this complication. So when you add a lot of code to deal that stuff instead of arrays, okay, what happens is you need to add a lot of code, and this is going to add a lot of code in the code segment and stuff like that. So eventually you want to save something like data segment. On the other side, you are wasting a lot of space in the other aspect in terms of doing that, and this is what going to take a lot of processing or compute power, and it wastes a lot of other resources. Okay, so always you can upgrade RAM. Always RAM is cheaper rather than upgrading the processor itself. What you do with the old processor, and moreover you can't use it anywhere. RAM, it is not the situation. I can buy a RAM for this laptop. Most probably I can use the same RAM for another laptop or something like that. So it is not the situation with the processor. Sometimes when you buy a laptops or any smartphones or something, what happens is they get soldered onto the motherboard. You can't anymore upgrade that processor. So that becomes a rare commodity versus something like RAM memory. And this you should take as a part of your design criteria, and this is how you, being an architect, or you have such opportunity in case you need to decide a specific architecture, you need to take this approach, you need to take this sense, and also you have to take that business aspects, and then you have to apply what is the best possible way, and not to stick with something which existed decades ago, and then try to follow the same principles which have been so said, taught which existed many decades ago. Okay. So take this clue. What you can do is you can experiment, try to put static allocation when you have any memory performance bottlenecks. Ditch away all sorts of dynamic allocation. This creates a lot of bottlenecks and lot of uncertainty. You get lot of runtime issues in the code, because essentially you are touching it runtime, and you are making it overcomplicated by putting all this runtime components. Okay, if you have an array, you statically know what you got the moment you run the code. If it is put in the execution mode, the moment you run the code, you get your allocation, and then with that what happens is you are ready and you are good to go. And assume each of this array slots are pre-allocated with that. Let's assume it is not array of pointers, it is instead array of data chunks. Let it be structs int whatever it is. Okay, so if you have something like that, what happens is the moment you insert this kernel module or kernel components, or else custom compiled kernel with this data structure, or else let it be user space global variable or anything actually. So once the moment you run it, what happens is you get the allocated memory. It is guaranteed. Now you can play around. You have full liberty to do whatever you want, and whichever slots you don't want to use. Of course, I have shot an episode about lookup table and stuff like that. So you can use some approach like that, and you can anyway avoid other cumbersome aspects of dynamic memory. And this is the basis in terms of if you are looking for something to improve the performance. First you need to ditch away something which you learned decades ago, and or else something which is written on the books, which is a learning standpoint which they got around decades ago. It is not going to work with modern systems and modern use cases, with our sort of requirements or things which we are dealing mostly these days. Okay.